So today we're going to start chapter 7. We're going to cover section 1, and section 1 is going to be covering angles of polygons. So the first thing we need to do is figure out what all the parts of a polygon are. So each segment that forms a polygon is called the side of a polygon. The common endpoint of the two sides is called the vertex. So in my polygon here, I have a vertex at A, B, C, D, and E. And then the segment that connects any two non-consecutive vertices is called a diagonal. So the green line here is the diagonal. Now, if I have a segment that connects two consecutive sides, so a segment that's going to connect two consecutive sides, that forms a side. So what I mean by consecutive vertices, E and D are consecutive vertices, and the connection here is called a side. But when the two vertices are non-consecutive and you connect them, that forms a diagonal. So right here I have a diagonal that's going from B to D because B and D are not consecutive vertices. I could also draw another diagonal from B to E. But when I draw it from B to A, that's consecutive, and this is a side. It's not a diagonal. Or if I go from B to C, this is also a side of the polygon. I can draw out diagonals from all of my vertices. So I could actually draw diagonals coming out of vertex A. I could draw a diagonal over here to D, and I could also draw another diagonal to C, because those are non-consecutive vertices. Again, where the endpoints of the two sides meet, that's called the vertex. And then when you connect two non-consecutive vertices, that connection is called a diagonal. And then the connection of two consecutive vertices, that's called a side. Next, we're going to go over the names for the polygons. So next, and we did this in chapter 1. So you can name a polygon by the number of its sides. The table shows some common polygon names. So a three-sided polygon is called a triangle. The general name for a four-sided polygon is a quadrilateral. And this is what we're going to be focusing on in chapter 7, quadrilaterals. In this section, we're going to talk about all of these. However, the rest of the lessons in chapter 7 are going to be focused on quadrilaterals. 5-sided figure is a pentagon, 6 is a hexagon, 7 heptagon, 8 octagon, 9 nonagon, 10 decagon, 12 is a dodecagon, and then the N down here, that's just the generic. Again, any number other than the ones in the table. Let's say it's a 50-sided figure. You would just put the number 50, a dash, and then GON. So any number that's not in that table, that's how you would name that type of polygon. Just put the number, a dash, and then GON. The next slide is talking about how we could find the sum of all of those angles. So it says to find the sum of the interior angle measures of a convex polygon, we want to draw all the possible diagonals from only one vertex. After we do that, it's going to create a set of triangles. We know that the sum of the angles of a triangle always is going to add up to be 180. So once I can form as many triangles as I can by drawing in diagonals from one vertex, I would add up the number of triangles I have, and then I would multiply that number by 180. So in the case of the triangle, I cannot draw any diagonals in here, because if I draw any kind of segment that's coming out of that purple vertex, the next connection I could make would be a consecutive vertice, which forms a side. And then same thing over to here. There are no non-consecutive vertices that I could draw a diagonal to in a triangle. So because of this, there's only one triangle here, and the sum of the angles of a triangle are 180. If I have a quadrilateral, and again, you're only going to draw a diagonal from one vertice. So if I chose that one, I can only draw in one diagonal because the other connections I would make would be consecutive. So this is 180 for one triangle, 180 for the second. You could either just do 180 times 2. And the sum of the interior angles of a quadrilateral are going to be 360. Now, I'm not going to expect you to draw in all these diagonals, count how many triangles you're forming, and multiply it by 180. I'm going to teach you a handy-dandy formula that will make things a lot easier. But again, in the case of the pentagon, from this vertex, I can draw in two diagonals, making three triangles. So two diagonals, which now forms three triangles, and I would do 3 times 180 and get 540. However, again, you're not going to have to do this. Instead, I'm going to teach you a formula on the next slide. So the next slide has a chart, and it's got the polygon name in the first column. It's got the number of sides in that polygon. Then it tells the number of triangles that you could form. And then the last one, the sum of the interior. You're just going to take the number of triangles that are formed and multiply it by 180. Now, the whole purpose of this table was to show you a pattern happening. All you need to do is memorize this formula that's down here at the bottom. It's n minus 2 times 180, where n represents the number of sides in your polygon. And this formula will give you the sum of all of the angles of your polygon. So let me show you an example with the triangle and with the pentagon. So in the case of the triangle, just applying this formula, for the triangle, we know that there are 3 sides, so that's my n value. I'm going to plug that in. We always subtract 2 from the number of sides. So 3 minus 2 is 1. 1 times 180. And the sum of the interior angles of your triangle is going to equal 180. Now, we already learned the triangle sum theorem, so really we shouldn't have to apply this formula to a triangle, but I just wanted to show you how it works. Now let me do the same formula, but now let's do a pentagon. So a pentagon, we can see in the chart that a pentagon has 5 sides, so my n value is 5. I'm going to do 5, always subtract 2 from the number of sides, and then I'm going to multiply that difference by 180. So I'm going to do 3 times 180, and this gives me 540. So the sum of the interior angles of a pentagon are going to all add up to be 540 degrees. We will not be using a calculator, so just make sure your basic multiplication skills are good. Okay, now the next slide actually has the formula officially presented as a theorem. So the polygon interior angles theorem just is telling us the formula. So the sum of the measures of the interior angles of a convex polygon is always going to be n minus 2 times 180. Then the corollary to theorem 7.1, which is the polygon interior angles theorem, is the sum of the measures of the interior angles of a quadrilateral is 360. So just like before, we memorized that the interior angles of a triangle are 180. Here you can also memorize that the interior angles of any quadrilateral will always be 360. Now, if you forget the corollary, you can always just use the formula. And then number of sides in a quadrilateral is 4. 4 minus 2 is 2 times 180, and you get 360. Now, this quadrilateral is any 4-sided shape. It doesn't have to be like a square or a rectangle. However, squares and rectangles their angles all will add up to be 360. Next, we're going to learn one more theorem. Again, okay, next we're going to define equilateral, equiangular, and regular. We actually saw equilateral and equiangular already with triangles. And when you see the word equilateral, that tells you that all sides are congruent. When you see the term equiangular, all angles are congruent. And when you see the term regular, that tells me that all sides and all angles are congruent. So it's both equilateral and equiangular. We're going to use the word regular a lot. So for example, you're going to see the word regular, and then they'll put it in front of a polygon name. So whenever you see the word regular in front of a polygon name, that tells you that all sides and all angles are congruent. The next slide, this is going to help you to get an easy answer on a test or a quiz, because whenever I ask you to find the sum of the measures of the exterior angles of a convex polygon, that answer, no matter what type of polygon it is always 360. So this is the exterior of the polygon exterior angle theorem. So just know that whether it's a pentagon, an octagon, a decagon, all angles in those polygons will always add up to be 360. These are the exterior angles. And the way that we could form an exterior angle is we would just extend the sides of our polygon. So for example, if we had a triangle, I could extend these sides going this way, and it would form exterior angles. And all of these exterior angles are always going to add up to be 360. So let's say this was a regular triangle, which is also equilateral and equiangular. So that would tell me all angles are 60. And know that the inside and the outside, or the interior and the exterior angle together, notice these are sitting on a straight line. So they're going to be supplements. So these exterior angles here would all be 120. And if I add them or multiply them by 3, notice you get 360. So again, you don't need to do any formula to find the sum of the exterior angles. Just memorize that the answer will always be 360. So if I said, what is the sum of the measures of the exterior angles of a decagon? You're going to tell me the answer is 360. If I said it's a hundredagon and I want the exterior angles, the answer is 360. So both of the formulas I've talked about prior to this slide were for the sum, when you added up all the angles. Now, whenever we want to find one angle in the polygon, and again, the key word here, it must be regular, because all of the angles inside would be the same. You're going to take your formula, your number of sides minus 2 times 180, and take it one step further, and then just divide it by the number of sides. So for example, in the case of the regular triangle, we know that n is 3. So if I do 3 minus 2 times 180, and then divide that answer by 3, which is the number of sides, 3 minus 2, 1. 1 times 180, I get 180, divide by 3. And one angle, or each angle in my regular triangle, would be 60 degrees. So this number is for each angle in my regular triangle. Now, if it's not regular, you could have different numbers. Okay, so example 1, they want me to classify the polygon by the number of sides, and then also tell whether the polygon is equilateral, equiangular, or regular, or it could be neither. So let's go ahead and take a look at, let me zoom in here to A. So notice all angles have the same congruency mark. All sides in this polygon have the same congruency mark. So this tells me it's going to be regular because all sides are congruent and all angles are congruent. So it's regular. And now I have to count the sides to figure out the name for it. So 1, 2, 3, 4, 5, 6 sides, telling me that this is a regular hexagon. Now you could also describe it as being an equilateral hexagon and an equiangular hexagon, but the better name would just be to put the word regular in front of the polygon name. The next one, notice there are no sides that have the same marks, and there are no, well, there's a pair, but I don't have all 4 sides here the same, and all 4 angles are not the same. So this is not equilateral, it's not equally angular, so that means it's also not regular. This is just a plain old quadrilateral. I can actually name it, but it doesn't get one of those special names as being equilateral, equiangular, or regular. It's just a plain old quadrilateral. Now, coming up, we're going to learn the special name for this one, and this is actually a parallelogram, and that will be in Friday's lesson. So this is a parallelogram. However, the general name here, it's got 1, 2, 3, 4 sides, making it a quadrilateral. Next, notice we have all congruent sides. So all my sides in this thing are congruent. So it's going to be equilateral. And now I'm going to go back and count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides, making this a dodecagon. Now, notice all 12 angles are not congruent because this is actually a concave polygon. So this would only be an equilateral dodecagon. It would not be regular because my angles are not congruent here. So I have a congruent angle here and here, but then the angle over here isn't, this is on the outside. So this would be the reflexive, so it would be like a 270 degree. Okay, so it's not, it's a concave, it's not convex. So it's only equilateral. So for example 2, it wants me to find 2 things here. It wants me to find the sum of the interior and then the sum of the exterior of both of these 2 polygon types. So for the interior angles, I'm using the formula n minus 2 times 180, where n is the number of sides in my polygon. So when I give you one of the special names, you need to know that a heptagon has 7 sides. So here my n value is going to be 7. So to answer part A, I'm going to do 7 minus 2 times 180. 7 minus 2 is 5. And now I have to multiply 180 times 5. And again, we will not be using calculators. So just make sure your basic skills here are good. So the sum of all 7 interior angles of a heptagon are going to be 900 degrees. For part B, I know that the sum of the exterior angles of my polygon here are going to be always 360. We're going to do the same thing for the 17agon. We're going to use the same formula. So for the interior angles, I'm going to do 17 minus 2, always subtract 2, 15 times 180, so 180 times 15, and I get 2,700. So the sum of all 17 angles of my 17gon will be 2,700. For part B, the sum of the exterior angles will always be 360 degrees. So that should be a freebie question on your test or quiz. If I ask you to find the sum of the exterior, there's no work, just memorize. It's always 360 degrees. So the next example wants me to find the number of sides of the polygon. So I'm still using the same formula, but this time I don't have the n. I'm solving for n. So again, I'm still using this formula, n minus 2 times 180. And remember, this equals the sum, but they gave me the sum. Now, I'm going to do this and solve this two ways, depending on how your Algebra 1 teacher taught you how to do questions like this. And again, I don't care which method you use, but on a test question or a quiz question like this, I'd like to see the work. So I'm going to set it up twice, just to show you that you have options. Or I could also solve it by, I'm going to rewrite the question here. So the first way is probably what a lot of you saw, and your teacher probably taught you to distribute. So I'm going to distribute the 180 to the n and to the 2. So I get 180n minus 360 equals 900. Now I have a nice simple two-step equation. I can add 360 to both sides. I get 180n is equal to 1,260. Divide both sides by 180. And the number of sides, once I do that division, will be 7. Now, the other way you can do this is whenever you have something set up like this and you have a parentheses and it's looking like you need to distribute something, I could get rid of the 180 first by dividing both sides before I distribute. And now I have n minus 2 equals 5. And then I just solve this by adding 2 and n equals 7. So this will always work. If you want to just divide the sum by 180 and then add the 2 to it, that will work as well. Either method would work. And again, you're going to need to be able to tell me the official name of a 7-sided figure, and you need to be able to tell me that it's a heptagon. So the last example here, it says to find the measure of each, this one wants not the sum, each interior angle and each exterior angle. So the two formulas we're going to be using are n minus 2 times 180 divided by the number of sides. This gives me each angle. And then for the exterior, remember it's always 360, but this time when we want each exterior, we have to divide it by the number of angles or the number of sides. So this will give me each exterior. So this one should have been each interior. So I'm going to use these two formulas. So for the first one, it's a regular quadrilateral. Now you could also use that corollary, and if you know that the sum of the interior angles of a quadrilateral are 360, you could just divide it by 4. But let me officially show you going through the formula. So I'm doing n minus 2. So my n is a quadrilateral, so it's 4. I'm going to divide it by 4. And I'm going to get 4 minus 2 is 2 times the 180, divide by 4. Now, we're still not using calculators. You can either decide to go ahead and multiply this as it is and then divide. And the interior angles of your polygon are all going to be 90 degrees when it's a regular quadrilateral. It's actually a square. And then to find the exterior angles, we're going to take 360, divide it by the number of sides, which is 4. And in this case, the exterior angles are also 90 degrees. This does not happen for all polygons. One thing to remember, like in the case of this regular quadrilateral, and it's a square, so the inside angles are all 90. And then when you go to extend the sides, notice the outside would also be 90, and realize that what we're forming here is a straight line. So these two together are always going to be supplementary. If after you do the math, and if you go back and add the interior plus the exterior, if those two together do not add up to be 180, you've done something wrong. Let's try the regular octagon. Same formula, but this time an octagon, my n value is going to be 8. I'm going to do 8 minus 2 times 180, and then divide that by 8. 8 minus 2 is 6. Now I can do it the long way and multiply 180 times 6, and I get 1080 divided by 8, and the sum, or each interior angle of an octagon is 135 degrees. That's the interior. For the exterior, we're taking 360, and we're going to divide that by 8. Once I divide 360 by 8, this gives me 45 degrees. And that would be my exterior angle. And again, if you wanted to double check it, quickly add 35 and 45, 135, and it does equal 180. So it's a little quick check to make sure you're doing it right. Now, since we're not using calculators, another technique you can do, instead of multiplying this here and getting this big number and then having to do the division, I could also take my 6 times 180, and I could look for things to simplify. For example, I could simplify the 6 and the 8 and make it 3/4. And then if you wanted to take it one step further, instead of having to do 3 times 180 and then divide it by 4, I could also divide 180 by 4, and this would be 45. And then I just have to multiply 3 times 45, which gives me 135. Again, whatever you prefer to do, if you'd rather just multiply it the way it is, do the 6 times 180, and then get that answer, the 1080, and then divide that by 8, it still gives you that answer as well. Either way. So for part C, 15 are gone, so 15 minus 2, it's always minus 2, times 180, divide by 15. So 15 minus 2 is 13. 13 times 180 gives me 2,340. And then when I divide that by 15, I get 156. This is my interior angle. Now again, if you want to simplify before you multiply, I could take this same problem, and instead of doing 13 times 180, I could also divide. 15 actually goes into 180 evenly 12 times. And then I'm just left multiplying 13 times 12, which also gives me 156. So whatever little tricks you want to do here, you can do things like that. For the exterior angle, we're going to do 360 divided by 15, and that's going to give me 24. And again, that's the interior. And again, you could double check it. If these two, when you add them, do not add up to be 180, you probably did something wrong with your multiplication or division. Then for part D, the 20 are gone. Same idea, 20 minus 2 times 180, divide by 20. 18 times 180, divide by 20. This one I would definitely probably try to simplify, like the 18 and the 20. I could make that a 1, make that a 9, and then I'm just left multiplying 18 times 9, and that gives me 162. And that's the interior. For the exterior, it's 360 divided by 20, and that gives me 18. So I'm going to add one more example to the notes here. You will probably see something like this. I don't know if it'll be on the test or the quiz or both. But let's say instead, I want you to find the number of sides in a regular polygon given that each angle equals 165.6 degrees. So in the past, my students have thought, oh, I can just guess and test and start plugging in numbers to the formula. The number I give you, you're not going to be able to guess and test. So you need to be able to work with the formula. So we're going to use the same formula we just did on the other slide. I'm doing n minus 2 times 180, divide by n, and remember this gives you each angle. So what I'm going to do is replace each angle here with 165, and I'm solving for n. So this is where we're using our Algebra 1 skills. Setting it equal to 165.6. So the first thing I want to do is get rid of my fraction. So I'm going to multiply both sides by n. That will cancel the fraction. I'm also now going to distribute the 180. So 180n minus 360 equals 165.6n. I need to get my like terms together, so I need to subtract the 180n from both sides. Notice my signs are different here, so I need to subtract 165.6 minus 180, or add negative 180, is negative 14.4n. I now need to divide both sides by negative 14.4. And now I'm left with n equals 25. So my polygon is a 25 gon, or you would just say 25 sides. So be able to find the number of sides in a polygon given either the sum, like I already did in the examples, or given the measure of each angle of the polygon. So be able to manipulate and work with the formulas. Straightforward, given an n, or given a sum, or given each angle. can also do the same thing if they gave us one angle of an exterior, each angle of an exterior angle. We could do the same thing, but we would work with the 360 divided by n.